Hello, everybody. We're going to talk about reading rocks. We learned a lot about how rocks form last time, and when we see how rocks form, we note that they can really tell us a story about what's going on in that particular rock layer and really tell us a history of what happened in that particular area. So we're going to discuss how we can do that, learn how to read the rocks, learn how to view the rock layers like pages in an Earth history book. To do so, first we're going to kind of introduce ourselves to geologic time and look at how things were put together through long periods of time over Earth history. We'll discuss the age of the Earth, and then we'll go through those processes that take us to the final product, which is the history of the Earth. We'll look at the relative dating techniques, looking at deposition and what formations are, the principles of horizontality and superposition, look at how tectonics affects the history of a rock series of rock layers. We'll look at cross-cutting relationships and fossils and unconformities. And this will give us a good indication of how to use the rocks that we're given to read them and interpret Earth history. We'll talk a little bit about how we can actually assign some dates to this and how we are able to use all this then to put together a geologic timescale. So here we go. Let's talk rocks and reading rocks. Let's first begin with trying to wrap our minds around what geologic time constitutes, because it's a lot of time involved there. We perceive time from personal experience in hours, days, weeks, years. Very infrequently we look at decades. When we think about geologic time, we're talking about millions and billions of years. This is how long it took landscape features to form in many cases, and as a result, it's really kind of hard to wrap our minds around that. English physician and farmer in the late 1700s named James Hutton made some pretty solid observations of his land in England, and what he noted was that in particular land areas and how the layers of rock worked, that the rivers and deposition that took place, the setting down of sediment that took place, would have taken a long time to get layer upon layer upon layer to get laid down. And you see a picture of his from his land there, and an artistic conceptualization of that above. But he came up with this idea called the principle of Uniformitarianism. He thought that if we know how rivers flood today and lay down sediment, then we can basically understand that that's how it's happened since the very beginning of the Earth. And as a result, some of these big, thick layers of stratum that are out there, those rock layers, would have taken millions of years to form. And so he couldn't put a number on the age of the Earth, but he said it was really old. And he said that the present processes today are the key to the past and how old the Earth is and how things operated in the past. So this is called Uniformitarianism. Hutton's ideas were in contrast to other ideas, popular ideas at the time, called Catastrophism. Bishop Usher is often credited with this type of thinking, in that the Earth began as a very with abrupt kind of catastrophic sorts of formations, and that would be kind of like based on a biblical chronology. He looked through the Bible and said that the Earth must have began sometime around 4004 BC, and kind of a more literal translation of the Bible there from him. And he also thought that major landscape features would have been created by single punctuated events like the biblical flood. Now these are kind of both of these ideas actually have a little bit of merit in that both slow, steady processes and singular catastrophic events can significantly shape the landscape. Picture in of the volcano here from Russia noted that this thing formed within a period of just a couple of months. So, large landscape features can be created in short amount of time. But also, large landscape features are created from single or slow, steady processes. When we talk about the actual age of the Earth then, current evidence from radiometric dating of meteorites and moon rocks suggests that the Earth and the oldest solar system materials are around 4.54 billion years old. To try to wrap our mind around 4.54 billion years old, I have a little activity for us here. If you imagine taking one calendar year and scrunching 4.5 billion years into one calendar year to try Let's now talk about the ways in which we can look at rocks and read rocks in order to understand what they're telling us about a region's past. Rock layers are called strata, and they can be analyzed to show the order of their formation to determine how old they are with comparison to one another. And in fact, they can read like stories or pages in a book of Earth's history, kind of like telling us the story of Earth's history. There are a few principles that we want to use to accurately read these rock layers. The first principle we have to kind of understand is that rock layers are deposited, so we need to think about environments of deposition. Layers of sedimentary rock, as we called them before, are strata, and they generally form underwater at different rates. Fossils present in the rocks also help us determine the particular environment of deposition. Examples might be swamps or bogs or marshes will end up forming rocks like shale because they're very, very rich soils with lots of organics in them. They end up forming muds, which eventually press into rocks that are like shale. Rivers would be more of a sandstone or conglomerate where you have the pebbles that you would find in the bottom of a river and sort of river sediment there. When it solidifies into rock, that's what you would find. Near shore or beach sediment would give us one type of sandstone. Desert or arid regions would give us a different type of sandstone. And reefs and shallow seas would give us limestone. And deep ocean would give us shales and limestones as well. And all these are different kinds and types. But the key here is that each type will give us and inform us on what type of environment we're looking at. If you look at how the rocks then are deposited, and when we go out and look at rocks, we're looking at them from the perspective of formations. A formation is a rock unit that has a distinguishable set of characteristics. And each formation, when you go out and look at, say, the rocks in Illinois, you can see pictured here, there's several different rock formations or rocks that have similar characteristics that we would group together. Each of them is given in a so-called stratigraphic column on a geologic map. Geologic maps give us and inform us on what types of rocks we're looking at and how old they are relative to one another. And rock formations are also named based on the area of prominence and the type of rocks found there. For example, the area around the Spoon River in Illinois, that formation is called the Spoon Formation after the Spoon River. So formations are groups of rocks. They are shown in relative age to one another in a stratigraphic column on a geologic map, and geologic maps show us those rock formations. And those names of the formations, they're based on the types of rocks or the types of features or the area that they are found in. Other characteristics of formations, they have to have a significant thickness. They have to be greater than a foot or up to hundreds of feet in thickness. They usually have a characteristic rock type that the whole formation maintains. Maybe alternating beds of sandstone and limestone, or just all sandstone or all limestone. And they sometimes have distinguishable fossils that are particular to that formation. And so fossils also help inform us on whether or not we should call a set of rock layers a formation or not. Any way you look at it, when we get these rock formations together and we look at them, how they're laid down, they are certainly laid down in specific patterns. And when we want to look at those patterns, we have to kind of look at them with a smart mind and some perspective. One sort of common sense idea that we need to think about is that layers are laid down horizontal. Sediment accumulates in near horizontal layers, and so when we see a set of rock layers, they should be pretty horizontal. If they're not, we note that something else may have happened after they were laid down. But this is called the law of original horizontality. Sediment accumulates in near horizontal layers. This is one of our common sense principles in order to help us to read the rocks accurately. The principle of superposition is another one of those common sense principles that says the oldest rocks must be on the bottom and the youngest rock layers must be on the top. When looking at a set of rock layers, it makes perfect sense that the oldest rock layers have to be on the bottom, because then they had to be there longer so that the younger ones could stack on top of them. So the oldest is on the bottom and the youngest is on the top. This is a principle of superposition. If a set of rock layers is tilted or folded or faulted or has igneous intrusions in them, we know that tectonic activity has taken place in this area. So that's another thing we can surmise when looking at the history of an area, that tectonic forces are also part of that history. There's also a principle called the law of cross-cutting relationships that says if an igneous intrusion or fault or river valley cuts across rock layers, then it's got to be younger than the rock layers it cuts across. The rock layers have to be there first before they can get faulted or intruded upon or cut down. So that's another kind of common sense principle that helps us determine the sequence of how things were put together and how things were made as far as the Earth's environment and the region's history is concerned. The principle of fossil succession or faunal succession states that different species or fossils appear in definite order within the rock layers, that we see certain types of fossils in different time periods throughout Earth history, and we see those then represented in the rocks. And so this is a very useful one as well, because we can pair rocks that have similar fossil assemblages and help us to determine how old they might be based on the fossils they have in them. One thing we really have to pay attention to in a rock sequence is if there is missing time. So obviously, every rock sequence is not going to be perfect. They're not going to be layer upon layer representing all time. You're going to have some missing things in there. The missing things, or the gaps or breaks in the rock record, those are what we call unconformities. These represent missing time in the rock strata. It's like somebody came and ripped the pages out of the Earth history book for these times. These may represent periods of non-deposition or periods of erosion, but in any event, they're important to consider. There are three types: the disconformities, non-conformities, and angular unconformities. First, disconformities. When you see flat sedimentary rock layers, and then you see an erosional boundary, and then more flat sedimentary rock layers above of a different type, or maybe even of the same type, you note that there is an erosional surface, you have a disconformity.
there's missing time. We don't know how long of time lapsed between the erosion of those layers below and the deposition of the layers above. If you have sedimentary rocks in contact with igneous rocks or metamorphic rocks below, this is what's often called a non-conformity. A non-conformity represents missing time in that we don't know how long the time gap was between the deposition of the layers and the intrusion of the magma, or the metamorphism of the rocks and then the setting down of the sediment. There's definitely some missing time in there when you have a contact between igneous and metamorphic rocks and then other stratified sedimentary rocks. This is a non-conformity. This last one is probably the easiest one to recognize. It's called an angular unconformity. This is where the rocks below make an angle with the rocks above. And you can see then the contact where the rocks below have been eroded away, and then the new rocks above have been laid down or deposited. So you can see that there's definitely some missing time in there. So those are important things to realize when looking at a sequence of rocks, are the unconformities as well. Okay, so gathering all our principles together of relative dating, we're going to try to look at some rock sequences and describe which ones are the oldest and which ones are the youngest. Here we have a rock sequence. It is a series of sedimentary layers and also some igneous rocks in there. So let's take a look. The first thing we note, and remember, the superposition tells us that the oldest is on the bottom and the youngest is on the top. So the oldest layer, the first layer laid down, had to have been R, sandstone. Perhaps there's a beach sand in the area for some time, maybe millions of years, and then maybe another set of millions of years where the water was a little deeper and you have more of an ocean mud sediment. That would be represented by layer V. So you have deposition of mudstone. Then perhaps a reef was in the area. In the shallow sea, a coral reef life began, and lots of limestone is deposited as a result. That would be layer S. And then you've got layer O. This layer O is kind of a unique thing. It's a lava flow on the surface, and it's within the stratified sedimentary rock layers. So this would be kind of a non-conformity with the rocks below and above. But we do think that O comes after S. Then we see layer F. Layer F is a basalt dike that kind of burns its way through the rocks at an angle. And we know that F comes in after R, V, S, and O because it cuts across them. That's the principle of cross-cutting relationships. We know that F comes in before H happens. H is an erosional event, probably, kind of causing those layers to be eroded in an uneven fashion. And F is eroded. It's cut across by H. So H comes after F. Then we have a period of sandstone deposition with N, a period of mudstone deposition with D, and then a period of limestone deposition with X. And so this is how the sequence would go, where we go R, V, S, O, F, H, N, D, X. This next sequence shows us a mudstone, layer C, being deposited, then a limestone, layer B, deposited, a sandstone, layer A, deposited, and all those layers had to be laid down first before D could burn its way through. That's a igneous intrusion there. And then E cuts across everything that's there, so E has to be last. So remember, the principle of cross-cutting relationship says that layers have to be there first before intrusions can come into them, and layers have to be there first before faults can break them apart. So D had to come before E, so E had to be the last thing. So it goes C, B, A, D, E. More sequence here. In this sequence, we have a limestone E laid down, then a layer G, then B. If you note, then all those layers had to be there first before the fault moves them. And then the fault gets cut across by that erosional surface there, A. F is deposited, and then finally C comes in at the end because C cuts across everything else. So C has to be last. So in this sequence, it would be E, G, B, D, A, F, C. In addition to relative dating, we also have absolute dating, ways to get the actual ages of rock layers. And when you combine relative dating with absolute dating, you can really get some great information about a region's history. Absolute dating then is defined as the method used to determine the age and years of a rock or other object, and it can be done in several ways. But what it does for us is that when we can tell one rock is older than another and get the relative sequence of rocks from oldest to youngest, if we can throw some dates in there, then we can actually get a readout of the history of a region very accurately. One way to find the absolute age of a rock is by measuring the rates of erosion and deposition. If you look at Niagara Falls, for example, on average, it erodes about 1.3 meters per year, and given its current position and projected starting point, we would find that Niagara Falls is about almost 10,000 years old. Likewise, you can use the age of deposition, the deposition rates to find age. If you look at the average deposition rate of the Mississippi River into the Gulf of Mexico through the Mississippi River Delta, you can see that it deposits sediment at about a rate of about 30 centimeters for every 1,000 years. The problem with both of these is that deposition rates and erosion rates can vary greatly. If you have a year where the water's particularly high, you're going to get a very fast erosion rate and a very ample deposition compared to other years. So this is a little bit, has some issues, but it does give us a general ballpark of how old something can be. Another way to tell the absolute age is by looking at lake bed sediments. You can see a rock sequence there in the bottom left corner. This person is looking at how the lake bed sediments that he's looking at were deposited over many, many years. And you can actually count them like tree rings. Each year, a coarse grained sediment is deposited in the spring and summer, and that because the water is moving fast. And then a very fine grained particle is deposited in the winters, in the fall and the winter, when the lake freezes over and everything's very still. All the sediment kind of floats to the bottom, and so you have a coarse and then fine layers of sediment each year. You can count these and it gives you an absolute age estimate. Some scientists actually also count the growth in tusks of mammoths. You can also, just like counting tree rings, you can get at how old something is and how long it was alive. And very useful also are ice cores. Scientists will drill a hollow drill tube down into the ground to pull out the ice, and they'll pull out a tube of ice, and that core has layer upon layer that has bubbles in it that sample atmospheric conditions every year all the way back to hundreds of thousands of years ago. So ice cores are very also useful in determining absolute age of things. And of course, one of our greatest tools is radiometric decay, radioactive decay in the form of radiometric dating. We know the rates of radioactive decay of many of the elements. Uranium and lead is one example shown here. But if we can compare the amount of radioactive to the amount of stable daughter product that is in a rock, we can tell how long it's been decaying, and using the decay rate we can actually get an age of the rock. And so this is a very useful tool in order to find the absolute age of rocks. Examples that we use: uranium-238 to lead-206, potassium to argon, carbon to... Using the absolute age, we can actually get a set of absolute dates for some of the rock layers within a sequence. Even if we don't have all of them, we can get a lot of good information. And putting together relative dating and absolute dating, we can take a snapshot of the history of a region. When we put together the relative sequence of rocks and we use the fossils that line up with one another and get some absolute ages in, we can correlate the rock layers of several areas and put together one whole, more complete sequence of the region. For example, if we go look at this picture here, in the bottom left is is by the canal. If we go by the canal, the river is cut into the ground a little and it's exposed the banks, and we see in the banks different rock layers and different types of fossils. If we go to a different part of town and to where the hill is exposed, we can find the same kinds of rock layers and fossils, and note that the bottom of the hill lines up with the top of the canal. And then further, we go to the quarry and find different fossils, assemblages, and layers. And we note that through correlating those layers, the quarry, bottom of the quarry lines up with the top of the hill. We can put together a whole section of history using correlation. If we combine then the relative ages of different areas around the region, along with absolute ages, we can get a very accurate history, even with ages of a region's history. Another example of this would be the Grand Canyon area. Further northward, when you get into southern Utah, you have beautiful national parks, Bryce Canyon, you have Zion National Park, all the way going down to the Grand Canyon. And each of these areas has exposed rock layers. As it turns out, Bryce Canyon represents the top of the sequence, Zion the middle, and Grand Canyon the bottom. Together, they give us a complete history, a complete look at what goes on, what went on for millions of years in this area. The big picture here, the final kind of summary here, is that geologists all have looked all over the world and done studies of rock layers and regions all over the world, and they've been able to correlate these with their relative dating and absolute dating techniques to put together a one-stop shop, one snapshot of Earth history called the geologic time scale. And this geologic time scale represents all of Earth history all the way back, very accurately, from the present all the way back to millions and even billions of years ago. And so we'll talk more about the history of the Earth learned from the studies done in our next segment on Earth history. So we learned to read the rocks today. We learned how geologic time operates on millions and billions of years, and how things are deposited, and how we can then use that information, some simple common sense principles, in order to read the rocks. We went through some examples of how we can do that, telling one rock older from another. And then we looked at some ways we can actually assign some dates to that through absolute dating of a few of the layers within the sequence. And then once we get all the information, we can correlate that with other areas to put together a whole regional history, or even a whole world history, Earth history, through the geologic time scale. So thanks for listening, and next time we'll talk about the history of the Earth through the geologic time scale.